Welcome to a screencast on osmosis. The objectives of this screencast are to describe the process of osmosis, to explain the reasons for osmosis, to perform calculations involving osmotic pressure, and to explain applications of osmosis. Now, this is our last colligative property. It's the movement of a solvent through a semi-permeable membrane, and it's called osmosis. Here we have a molecular level image of what's going on. This is the semi-permeable membrane. A semi-permeable membrane is one that allows the passage of solvent molecules typically, but not of solute molecules. So here our solvent is water. Our solute particles are these green ovals. And we could imagine a semi-permeable membrane essentially as having openings that are small enough to let water molecules through, but too small to let solute particles through. This isn't exactly what's going on. This isn't a perfectly accurate representation, but that's a way to sort of think about it. So solvent molecules can go through the semi-permeable membrane. Solute particles can't. Now, if we have a semi-permeable membrane in the middle of a U-tube like this, and on one side we have some pure solvent, let's say water, and on the other hand we have a solution, and here the blue spheres represent solute particles. If initially the levels of the solvent, pure solvent on the left and the solution on the right are equal, what happens is water molecules, or whatever the solvent molecules are, they can go through this semi-permeable membrane in either direction, from the pure solvent side into the solution, or from the solution side into the pure solvent. But the solute particles can't get through the membrane. They aren't able to pass. Now, essentially what's happening is on this side we have 100% solvent. On the other side, the solution side, we have less than 100% solvent. Maybe let's say it's 95% solvent. So we have a higher solvent concentration on the left here than on the right. And since there's a higher solvent concentration, more solvent molecules per amount of time will pass from left to right through the semi-permeable membrane than solvent molecules will from the solution from the right into the left. And you're going to therefore have a net flow of solvent from the side with the pure solvent, in this case, but in general from whichever side has a higher solvent concentration, into the side that initially has a lower solvent concentration. Now note, this is also from the side that has the lower solute concentration into the side that has the higher solute concentration. And this net flow of solvent molecules is going to lower the volume or decrease the volume on this side, increase the volume on the other side, and this is the process of osmosis, and osmosis continues until the pressure due, in this case, due to the height of the extra height of the column of now diluted solution on the right-hand side, until the pressure due to that extra solution above this level, until that pressure is enough to essentially stop the net flow or make the net flow zero, depending on how you want to look at that. So we still have 100%, in this case, solvent on the left-hand side. It still has a higher solvent concentration, so we still have, per moment time, more solvent molecules that want to cross from left to right than want to go from right to left. But eventually, there's just enough pressure from this side to stop that net flow, and so the flows in both directions are equal, and we end up reaching equilibrium. So Osmosis continues until the osmotic pressure is large enough, and we'd say the amount of pressure needed to stop this movement of solvent and achieve equilibrium, we call that osmotic pressure. We symbolize it by the Greek letter pi, capital Pi, and the relationship between osmotic pressure and other quantities is shown here. Pi equals mRT, where pi is the osmotic pressure, m is the molarity of solute particles, and so in here we have to take into account concentration in moles per liter, but we also have to take into account whether there's any dissociation, so the Van 't Hoff factor I comes into play. R is the universal gas constant, so 0.0821 liter atmospheres per mole Kelvin, and T is the temperature, and the temperature has to be in Kelvin. So osmotic pressure is directly proportional to solute concentration, total solute concentration. An example of osmosis, if we have a substance here that has a semi-permeable membrane around it, so this dotted line represents a semi-permeable membrane, and inside this thing we have a lower concentration of salt ions, so these black spheres represent salt, which is our solute here, and on the outside we have a higher concentration of solute ion particles, in this case salt ions. Well, since the water concentration, we're going to assume this is an aqueous solution, since the water concentration is higher inside this this sort of strange shape here than it is outside, then the water, the solvent, will have a net flow from inside to outside. It effectively ends up diluting this outside, more concentrated in solute solution. And over time, what ends up happening is, since water flows out of this, it gets smaller, and the solute concentration outside of this decreases, and eventually the net flow stops when osmotic pressure is large enough. And this is an actual thing that happens if you take a cucumber, and basically we can think of cells as essentially having semi-permeable membranes around them, and so the cucumber functions that way. And if we put it in a brine solution, a highly concentrated salt solution, what ends up happening is the cucumber shrinks and it eventually turns into a pickle. Now, of course, a little more is going on here in making a pickle, because some substance, actually some salt, gets absorbed by the cucumber when it's turning into a pickle, but the reason, at least for the decrease in volume, is because of osmosis and water net flowing out of the cucumber as it becomes a pickle. Okay, and a practice calculation with this. Normal intravenous saline solution is 0.90% weight to volume NaCl. And the question is, what's the osmotic pressure of this normal IV saline solution at 25 degrees Celsius? And of course, if we're dealing with finding osmotic pressure, we should use the osmotic pressure equation. R is a known constant. T is given, temperature in Celsius here, we convert to Kelvin. So essentially this hinges upon getting our molarity, and we're given it's a 0.9% weight or mass to volume solution. That's the W/V, what that stands for. And this would be, for example, 0.9 grams of NaCl, that's saline, or what makes it the saline is the NaCl dissolved in water, in 100 milliliters of solution. So 0.9 grams, percent means out of 100, and since it's mass or weight to volume, it's in 100 milliliters of solution. Well, 0.9 grams, fairly easy to convert into moles, 0.0154 moles, And then remember that NaCl, when it dissolves in water, it dissociates into two particles. So we have 0.0154 moles of NaCl, but it gives us twice that many moles of NaCl particles. And then, of course, 100 milliliters is 0.1 liters. So that's going to be our solute molarity. And so now if we plug in all our values, 0.0154 times 2 is 0.0308. That's the solute number of moles. The volume, 0.10 liters, and moles per liter gives us our molarity. Gas constant is 0.0821 liter atmospheres per mole Kelvin, and 25 degrees Celsius is 298 K. Moles and moles cancel, liters and liters cancel, Kelvin and Kelvin cancel, leaving us with just units of atmospheres. And when we do the calculation and then round off to two significant figures based on the initial information we were given, we get about 7.5 atmospheres for the osmotic pressure of normal IV saline solution. And one more note, if we go back to our normal osmosis situation, our U-tube with pure solvent on the left and a solution on the right, semi-permeable membrane in between, normally there'd be a net flow of solvent through the semi-permeable membrane from pure solvent to solution, decreasing solvent volume, increasing solution volume, and this side of the U-tube would increase in volume, and it would only stop when the column goes high enough such that the pressure due to that overcomes the net pressure due to the flow, osmotic flow, and eventually we'd reach equilibrium. Now, the other thing that can happen is we can actually add pressure in the opposite direction, so we can apply pressure that's more than the osmotic pressure on the right side of the U-tube, and if we apply more pressure than is due to the osmosis in the normal direction it would flow, we can essentially squeeze or force water to go in, or whatever our solvent is, to go in the opposite direction to what it would normally do. And so in this case, we'd force water to go through the semi-permeable membrane from right to left, from the solution into the pure solvent, in the opposite way of what would be normal. And this has a very practical application. It's called reverse osmosis because we're reversing the normal direction of osmotic flow. And in reverse osmosis devices, what ends up happening is you can actually take salty water, impure water, and squeeze the pure water out of it and produce pure water. And so this is very useful in places where there's maybe salt water available, but not much pure water for drinking or irrigation. This is a way to get that. Now, it's a little bit challenging because it requires high pressures and membranes, semi-permeable membranes that can withstand those high pressures, and it requires a fair amount of energy to make this process occur. But this is done in many parts of the world as a water purification method. And that's it for the Osmosis Screencast.